Hello, my friends. Welcome to Origins. My name is Don Chapman. It's my privilege to be your host. We like to say that Origins is a forum where we use the evidence of science to validate the truth of creation. We have an incredible guest with us today. His name is Dr. Larry Vardiman, and he is a atmospheric science PhD from Colorado State University, and he's a member of the American Meteorological Society. Dr. Vardiman, welcome. It's good having you with us. I mentioned your credentials from the American Meteorological Society because we're going to talk today about a term that is new to me, hypercanes. Now, what I think of first of all is hurricanes, but what's a hypercane?
Well, it's basically a glorified hurricane. It's a giant hurricane that has grown over very warm water and gotten extremely large and extremely energetic. Lots of high-speed winds, a lot of rain. It's just a giant hurricane.
People are fascinated by hurricanes, and I think one of the things we maybe need to say first is that you aren't expecting any of these soon, are you?
No, I wouldn't expect them today. We don't have warm enough surface waters over a large enough area to produce a hypercane. We can come close to that. We have Category 5 hurricanes. We've had a number of those in the last few years, but hypercanes are something beyond that, 2, 3, 4 times more intensive than they are.
Let's put this in a historical context. You believe that hypercanes did happen.
Yes, I believe they happened in and immediately following the Genesis flood.
So this is one of the results of the Genesis flood were hypercanes.
Yes. A hurricane, or a hypercane as we're going to talk about, basically is energized by the temperature of the water over which it rides.
Okay.
The surface temperature, the hotter it is, the more water vapor it puts out, and the water vapor is like gasoline for an engine. It's the fuel that drives a hurricane. So if you have extremely high surface temperatures on the ocean, it can produce hypercanes. And in fact, the term hypercane was introduced first by a gentleman, a professor at MIT, and by the name of Cary Emanuel. He actually has published on this subject and has developed the concept of a hurricane or a hypercane being a thermodynamic engine, where the surface temperature is one reservoir, heat reservoir, and the top of the hurricane is the cold reservoir, and the bigger the temperature difference between those two, the more energetic the hypercane is.
So today, when we're looking at is it going to be a bad hurricane season, one of the things that I always hear them talk about is the temperature of the water in the southern Atlantic. That's right? That's
right. And every time you see high temperatures, that's why the hurricanes occur typically in August and September and October. That's when the ocean temperature is the hottest.
And the hotter that water, the more fearful they are that we're going to have more hurricanes and bigger ones.
That's right.
And so how hot was the water after the flood?
Well, I think the water could have been as warm as 90 to 120 degrees Fahrenheit. The hottest temperature we see today typically is in the tropics, and it gets up to about 90 degrees Fahrenheit. But right. I believe that it was 90 degrees to maybe 120 degrees Fahrenheit worldwide immediately after the flood.
And so the climate was right, the water was right to create these incredible storms.
That's exactly right.
Well, we're anxious for you to help us understand them.
Okay, well, let's start first with a satellite image of Katrina. I think most of us are familiar with that hurricane. Occurred a few years ago, came from the Gulf of Mexico and intersected Louisiana right at New Orleans. Here's a picture right as the hurricane was intersecting New Orleans. And it was a Category 5 when it crossed the coast into New Orleans. That's why there was so much damage caused by this hurricane.
Category 5 is 150-mile-an-hour sustained winds.
That's right.
Yeah.
And so it's a very, very intense hurricane. But the hypercanes we're going to talk about are even more intense than that. Here's a picture also of Hurricane Katrina. However, this is an infrared picture as opposed to the previous one, which was a visible picture. Using infrared technology, you can estimate what the surface temperature of the ocean is. Here, the colors indicate what the temperature is. In the upper part of the picture near the north, we have blues, which you can see from down here on the order of 20 degrees centigrade. That's about 70 degrees Fahrenheit. So you're not going to have many hurricanes that form in that cold of water. But down in the Caribbean and in the Gulf of Mexico, it's turning more yellow, and particularly around New Orleans at that time, it was in the oranges almost to red, which is right at 30 degrees centigrade, which is better than 90 degrees Fahrenheit. It was like bathtub water practically when Katrina crossed into the north part of the Gulf just before it hit New Orleans. So it accentuated or amplified dramatically into a Category 5 hurricane as it approached New Orleans, was right at its peak when it hit New Orleans. So you can see from this and from other hurricanes that we've seen since then that the amount of energy that energizes a hurricane comes from the temperature of the surface of the ocean beneath them. Now, I've taken this concept and applied it to some research and looked at the details of a hurricane. Here's another hurricane. This is Hurricane Dennis that occurred back in 1999. And NASA Goddard in Maryland has taken hurricane pictures or satellite images and displayed it sort of as a perspective drawing and animated it. So you can actually see the eye in the middle, you can see the eye walls, and it rotates around the center. So we have a lot of information about hurricanes and details that really help us to understand how they function. And the idea of what makes them tick in terms of temperature is really fascinating because of how fast they will amplify and become severe. I took a hurricane from back in the 1990s called Hurricane Florence. Now, we had one not too long ago with that same name. They repeat the names every once in a while. But this was an earlier hurricane that had a very similar path to that of Katrina. Actually, it started just north of the Yucatan Peninsula down here and was kind of meandering around for a while. But then it started heading north, and the temperature in the Gulf of Mexico at that time was not extremely warm, and it was fairly uniform, and it did not amplify or did not die out. It just kind of slowly migrated northward and crossed over New Orleans, very much like Katrina did. But it never reached Category 5. It stayed about a Category 1 or Category 2 because the temperature of the water surface in the Gulf at that time was relatively cool, and it was uniform throughout the Gulf. So the track of this particular hurricane headed from the Yucatan Peninsula and up and crossed into New Orleans and didn't do hardly any damage at all. What we were able to do then was put the information from this particular hurricane into a computer model and simulate. It's called Mesoscale Meteorology Model, MM5 for short. And we were able to use that and simulate the actual path of the hurricane and the characteristics that it had, just like the real one. And then we changed the boundary conditions. We put in the sea surface temperature much hotter, different levels of temperature, 5 degrees centigrade, 10 degrees centigrade warmer than what it actually was.
So you made a computer model and changed the temperature of the water and saw what the damage would be. Is that
right?
We're
using a conventional numerical model and changing the boundary conditions to conform to what we think might have happened, like following the Genesis flood. So this hurricane, when we did that, began to amplify and increase in intensity and get bigger. And here are some of the features of it before we show the whole thing in an animated form. This, for example, is the blow-off at the top of a hurricane. The hurricane is relatively small in diameter down near the base, and it gets bigger as you go up to the top, and it blows out the top and produces this gigantic cloud called an anvil, or a blow-off region, and it's typically ice crystals up there. Okay. And this is the boundary of that blow-off region. You can see here where it started. It was a relatively small hurricane down here, initially just north of the Yucatan Peninsula, and we simulated what would happen every hour for about 34 hours. Now, we actually went a total of 34 hours, but for about the last 10 hours, it exceeded the boundaries of the box that we had put in. So I'm only going to show for about 16 hours here. And you can see it grows and gets bigger. These are concentric circles. Each one of those is 1 hour up to 16 hours after it started. And this is the Gulf of Mexico here, basically. This is the Gulf of Mexico as it started. And this is the southeastern United States, Florida and up the Mississippi River and on up toward the northeast. Well, you can see this hurricane took over the whole Gulf of Mexico and the whole southeastern United States. Right. And it grew into a gigantic hurricane in a very short period of time. Only 16 hours it grew that big. This is actually a graph. If we found the area of all those circles and plotted them as a function of time, this is the area of the circles in millions of square kilometers as a function of the start point out to 18 or 16 hours. You can see that it increased slowly at first and then started to accelerate in its size. So it grew very, very rapidly near the end. It was just getting gigantic. Here's another measure of the intensity of the hurricane. It's something called vorticity. It's actually a measure of how fast the hurricane goes around in a circle. It's kind of like a merry-go-round. You can measure how fast a merry-go-round because it's a solid platform. In the atmosphere, it's a fluid or a vapor, and so you have a different measure of that, so it change a little bit as a function of radius, but vorticity tells you how fast it's going around a circle. And this hurricane started with a measure of vorticity, which I won't describe the units on, but starts at a relatively low value and goes up slowly and then reaches a peak value up here that's something like 8 times more rapid going around in a circle than what it started as. So it not only got bigger, but it was also going around. It was wrapping up and getting faster and faster. Okay, then I did a simulation of this showing it in perspective. What we actually started doing was I increased the surface temperature of the water, and you can see here actually an artificial boundary. I made a region that was warmer, kind of a box or a rectangular shape, and made it at various temperatures like 30 degrees centigrade, 40 degrees centigrade, 50 degrees centigrade, and let the model grow the hypercane, actually started out as a hurricane, grow into a hypercane, and it grew larger and larger and more intense. Now the yellow region that you see here on the outer boundary of this is the cloud boundary. And inside of that, the green region here is the rain. So we actually have a larger boundary, which is the entire visual part of the hypercane that you can see as if you were flying an airplane to it. The outer part is the cloud, and inside of that is the rain shafts. And the rain shafts became very intense, and as the hypercane actually began to spin here, these rain shafts actually bent over and twisted around and moved around, very much like a tornado in a sense, but it's it's a big hurricane, and typically would have a hole in the middle called the eye.
Sure.
So it's a very intense, and the winds around this, we'll talk about in a minute, they got extremely fast. The vertical speed got extremely fast, and the amount of rainfall that came out of such hurricanes, hypercane became very fast. The coverage of this, you can see, is rather dramatic. It fills the whole Gulf of Mexico before it's over and covers the whole southeastern up to the Rocky Mountains there. Now you'll notice at the end of this, it's starting to get kind of sharp edges around it. This had a particular finite size to the simulation. It was bounded by a box that we built this in. It was an artificial simulation. So as the thing extended upward, it extended out the top of my box, and we had an artificial flat surface, and the boundaries of the box here caused it to kind of truncate or be sharp at the edges. So as long as you don't try to worry about too much of the details around the edges or at the top, you're okay, as long as you get away from the boundaries of your simulation. But this gives you an idea of how a hurricane, if it moves into the right locations where there's a hot sea surface temperature, it absorbs that energy from the ocean, energizes the clouds that are built into it, and causes the whole thing to start rising and circulating. So it's a major heat engine, or a thermodynamic engine, as Kerry Emanuel says.
How fast would those winds be going in your model?
Okay, a really high-speed hurricane, the horizontal wind speeds might be as much as 100 or 125 miles an hour, maybe 150 miles an hour.
Category 5, I think, starts at 150
miles an hour.
Top, right?
Typically, the hypercane will be 4 times that. So you could be 500 or 600 miles an hour. If you take a Category 5 hurricane and get it in the right conditions, it could be reaching 500 miles an hour.
That's incredible.
It's amazing, isn't it?
Now, when we see the devastation from a Category 5 hurricane, I think Katrina was 4 when it hit the shore. It was 5 just until it got there, maybe went down to 4, but so it was maybe 140 to 150 miles an hour. And it's going to be decades, if not years, maybe decades or at least many years until they can recover from that.
Yes. You can imagine what the hypercane would do?
There would be nothing left virtually, would there?
No. I mean, it would just wipe everything off that's above the ground surface.
And even some of the ground.
Yes. In fact, the precipitation rate from a hypercane we have computed is about 10 times what a hurricane would be. So if you're getting something like 5 inches per hour from a hurricane, you might be getting 50 inches an hour from a hypercane.
So 50 inches an hour of rain.
I mean, we're talking about major downwash of water, and surfaces under that would be eroded incredibly, particularly if it stands in one place very long.
And you were telling me in the green room that not only do you have the rain coming down and the rain the wind that's going east and west, but there's an updraft as well?
Yes. In the wall surrounding the eye is where the most intense vertical motion is. And that motion in a typical hurricane is on the order of 40 or 50 miles an hour, and the vertical motions in a hypercane will be at least twice that. So you could have a 100-mile-an-hour wind going vertically in these thunderstorms in the hurricane.
So it would almost be a tornado force or more.
Yes, it becomes as intense as many tornadoes are.
Yeah.
But much larger.
It's mammoth in size.
That's right.
Now, I think we understand a hypercane. I understand it enough to not want to be in one. I'm telling you that for sure. We'll put this into the situation with the Genesis flood and the impact that it had and the consequences it had. Don't you go away. We'll be right back.
Creation versus evolution. You weigh the evidence. Random mutations, fabulous fossil folly. According to evolutionists, we exist because random mutations turn simple organisms into more complex creatures. If so, where are all the leftovers and mistakes? Where are all the fossils showing evolution? Through the years, we've been exposed to many hoaxes, but we haven't found one evolutionary fossil. Instead, we see millions of fossils that actually indicate creation of many distinctly different species at one time. Today's guest on Origins, Dr. Larry Vardiman, is chairman of the Department of Astrogeophysics at the Institute for Creation Research's Graduate School. Through his ongoing research in atmospheric science, Dr. Vardiman has contributed much to the field of creation science. He also led the RATE team, a research project examining the age of the Earth. This has been documented in the DVD Thousands, Not Billions. For more information, contact the Institute for Creation Research, 1806 Royal Lane, Dallas, Texas, 75229, or call 1-800-337-0375, or visit the website www.icr.org.
We're back with Dr. Larry Vardiman, and we're looking at hypercanes and the impact that this mammoth, hurricane on testosterone would have. Dr. Vardiman, help us understand your conclusions from this model that you drew.
Well, first, the first conclusion, which is very satisfying, is that I believe that we successfully modeled these hypercanes using this conventional model called mesoscale meteorology, or MM5 for short. We were able to actually do that unless the surface temperature got above about 50 degrees centigrade. Then the model couldn't handle it. So we were able to handle hypercanes for sea surface temperatures up to about 120 degrees Fahrenheit, and beyond that it didn't work. We also found that high sea surface temperatures, that is greater than about 30 degrees centigrade, which is 90 degrees Fahrenheit, would form hypercanes. You get hurricanes up to about that temperature, and then if you have sea surface temperatures warmer than that, the hurricanes just explosively grow to bigger ones, which we call hypercanes. So the hotter the temperature, the more energetic and the larger they are, and the more damage they're going to do. We also found from this simulation of this Hurricane Florence growing into a hypercane that it actually quadrupled the horizontal wind speed. That means it's 4 times as fast as this Hurricane Florence was, just by increasing the sea surface temperature. We found that the vertical wind speed doubled just by increasing the sea surface temperature. And that happened very rapidly, just within 16 hours or so. It increased the precipitation tenfold, which is really dramatic because hurricanes quite often will have 2 to 5 inches an hour, maybe occasionally 10 inches an hour. And if you increase it by a factor of 10, you're having tremendous precipitation rates.
So can you imagine having 30 or 40 or 50 inches of rain falling in an hour?
I mean, it would just flood like crazy.
It would
have a
like
major
crazy.
devastation.
Yeah.
And finally, the last conclusion I have is that if the sea surface temperature globally was as warm as I think it was following the Genesis flood, you were likely to have these hypercanes all around the globe, covering the entire Earth for at least a number of years after the flood.
How long did it take the ocean to cool off after the Genesis flood?
I think it took about 1,000 years for the sea surface temperature and the ocean itself to cool from this hot state that we believe it occurred right after the flood down to close to what we have today.
And 1,000 years.
Right.
And so during that period of time, more at the beginning and a little less at the end, though, it would be on a continuum, but there would be the conditions for these for a long time on the earth.
Right, particularly right after the Genesis flood, when the ocean was the warmest. It would cool off the fastest right initially. It's like if you take a cup of coffee and put it out on the counter, it cools exponentially, initially cooling very rapidly and then slows down to reach an equilibrium temperature. So within the first tens or hundreds of years after the Genesis flood is when you would have most of these hypercanes.
Now, we're filming this show in Pittsburgh, and our weather usually comes from the west. That's the way the wind usually blows here. That's right?
In mid-latitudes, the climate in the northern hemisphere, the winds come from the west. In fact, even in the southern hemisphere at mid-latitudes, it comes from the west. But down in the tropics or the subtropics, the surface winds come from the east. So that's why we have hurricanes that come across the Atlantic from Africa,
right,
develop and grow, move into the Caribbean and the Gulf of Mexico where the water is the warmest, and hit the coastlines.
Do you believe that the surface winds today are similar to what they were after the flood?
Yes, generally they were pretty much the same, except that the winds, particularly the jet stream aloft at mid-latitudes, could have been as much as 50% faster than today.
But still the same patterns?
Basically the same pattern. The jet stream would probably have been a little bit further south so that the tropics may have been squeezed a little bit, but basically the same pattern, yes.
So could you tell us from that where you think hypercanes would have hit most often?
Well, generally in the tropics and subtropics, the hypercanes would have hit the southeastern part of the United States and basically along the eastern side of the continents, either here or in Southeast Asia, any place on the east side of a particular large landmass in the subtropics. In the mid-latitudes, like up around 30 to 45 to 60 degrees north, the hypercanes, if they formed out over the oceans,
which they
would have moved eastward, coming from the west to the east and hit the continents on the west side. My thought is that right after the flood, the surface of the earth would have been very bare. There wouldn't have been much grass, there wouldn't have been shrubs, certainly would not have been large trees. So if you had hypercanes with this tremendous devastation, particularly with the high rainfall rates, falling on sediments that are not even turned into rock yet, unconsolidated sediments, you would have an incredible amount of erosion. And I believe that there is evidence for that, particularly like in the southeastern United States and the Appalachians. We know that the Appalachian Mountains are highly eroded, very unusually so compared to the Rockies, for instance. Now there's various explanations for that, but this may be one of those. Another one is in Southeast Asia. There's a tremendous amount of erosion that occurred there. And there are other places around the world where maybe the hypercanes are the explanation for this.
So what's the significance of this? What's the takeaway for us today?
Well, I think the takeaway is that conditions immediately following the flood didn't just suddenly become calm and quiescent and peaceful. Noah, if he and his family had gone down into the tropics, would have probably been devastated by hypercanes. They were in the middle of a continent near Mount Ararat, and they had their own challenges because even on Mount Ararat, things were cooling and snow was chasing them off the mountain. But they were more or less safe from the simulations that I've done. But there's a lot of erosional features that we may be able to explain by hypercane formation and the devastation that they produced, not just simply by other features that we have to look for.
The flood and its after effect was more of a catastrophe than I think most of us often realize.
It's incredible. There was a lot more going on than simply a lot of rain and water coming up and down. Continents were being affected, earthquakes, volcanoes, hypercanes. There's just a lot that went on, not only just during the flood, but for some time after the flood. The whole Ice Age, in fact, I believe was due to consequences of the Genesis flood.
God was really rocking our world, wasn't he?
He was.
I'm so thankful today we don't have to live through hypercanes. Hurricanes are big enough for me. But I want you to know this, that the place we always need to live is in the palm of God's hand. That's the place where it's safe. When we are walking with Him and obeying Him and trusting Him and believing Him, that is the greatest place to be. I hope that's where you're living. And I hope above all, until next time, you'll remember this. It's God's view that He created you. And that should be your worldview too. Hope to see you again here on Origins.
Thank you for watching this edition of Origins. If you'd like a copy of the PowerPoint information presented today, you can download a PDF file of program number 801 from our website at www.originstv.org. Or for a DVD of this series, send a $12 donation to cover shipping and handling and write to Origins Program, number 801, Cornerstone Television, Wall, Pennsylvania 15148.
Origins is made possible by the faithful prayers and the financial support of you, our Cornerstone Television family.